We continue now with the last two reactions. The first one, the last two, is called Friedel-Crafts acylation. Okay, so again, let me do this example, assuming I have the ring of benzene, and on the ring of benzene I will pour the following substituent, C double bond OH. Okay, it's a substituent, and I open the table will tell me that C double bond OH is a deactivating substituent. So I'm expecting now to know that the product must be meta. So this compound is reacting with another compound that you will learn in Orgo 2, which is CH3 C double bond O Cl. This one is called acyl chloride, acetyl chloride, okay, acyl chloride. Again, in presence of the Friedel-Crafts catalyst aluminum chloride will give us, this is the ring of benzene, C double bond O and an H on this carbon. So in meta position, you're going to attach C double bond O CH3. Okay? So these two substituents, as you notice, they are in meta position plus HCl. Mechanism. Step number 1, formation of the complex. So I'm gonna use this CH3 C double bond O in bond with the chlorine. Reacts with the aluminum Cl3. Alright, again, this is fast. This is the Lewis base. This is the Lewis acid. You take 2 electrons, attack. Motion number 1. We get CH3, C double bond O, the Cl here positive charged, the aluminum negative, Cl3. And so this is our complex. Step 2 would be formation of the rhenium ion. So I take my benzene, C double bond OH is reacting with the complex CH3, C double bond O, Cl with the plus, aluminum minus Cl3. And that's the slow step. Because it needs to be in meta position, okay, I cannot use this bond because this bond will make me only use the ortho. So the bond that I'm going to use is this one, motion number 2, goes on this carbon, and so you release in motion 3 the chlorine. The rhenium ion is this, C double bond OH, you keep the double bond here. Now the carbonyl, the C double bond O goes here, remember you have an H, so on this carbon you have a plus, and that's the rhenium ion. Plus you form Cl, still in bond with aluminum chloride negative charged. Step 3 will be restoring the ring, so you copy this all over again. There will be double bond, C double bond OH, then you have here C double bond O with a CH3 and an H, plus, and a double bond, plus Cl, aluminum negative, Cl3. Fast and in presence of heat. This is the bond you break. Motion 4. The Cl grabs the H. Motion 5. The H restores the ring in motion 6. Identical. So you get the ring, double bond, C double bond H. We have the C double bond O CH3 You get the ring and the ring. What else? HCl plus aluminum chloride. Okay, as you can see, these three mechanisms are absolutely the same. The steps are the same, so everything looks the same. So now, why I have this substituent is meta. Why meta? We start again from the rhenium ion. The rhenium ion was this. Double bond here, C double bond OH, this is C double bond OCH3 and an H. Let's play with resonance structure. Flow these electrons in this position. You have the plus goes here, C double bond OH, you still have the H, you have the C double bond with the CH3. Moving this, I get C double bond O, the double bond goes here, there is a plus, there is an H, C double bond O, CH3, double bond. And that's it, no more than this. These are the three resonance structures. Is anything here very impressive? Quite frankly, no. I don't have a tertiary carbon cation. I don't have one of the very stable solution that I saw before. So, but now let me show you why no ortho. Let me see why cannot be ortho. I'm starting again from the rhenium ion, C double bond OH. Here, because I want to have a ortho, supposed to be C double bond O, CH3 and an H. So now, because it was supposed to be ortho, all the rest here, and so this is the carbon with the plus. Let's play with our resonance structure. I'm playing this C double bond O, then you have a C double bond O CH3 with an H, this one stays here, and you have a plus. I still have another one, you flow these guys around, so the plus goes here, that's the H, C double bond O CH3, and then you have here the double bond with the C double bond OH. So these are the three possible resonance structure. Let me put the plus. If you play, so you go back to these three. What's the problem here? One of these resonance structure is extremely unstable, and it's this one. Why? Because on this carbon you have a net positive charge. When you go outside, you have the carbon and the oxygen. You learn in chemistry 1, oxygen is very electronegative, so we give to the oxygen delta minus. The carbon is less electronegative, so you give a delta plus. So what's the problem here? The problem is that you have a plus and a delta plus, meaning you have two elements, both positive, means that here there is instability, there is repulsion. Okay? Because of this repulsion, this one becomes the most unstable resonance structure. Okay? So in case of this substituent, it can never be ortho, and you show again why cannot be para, because of this most unstable resonance structure. Okay? So I'm going to do the last example, the last reaction, which is called nitration. of a benzene, of a nitration. Okay, nitration means addition of HNO3, nitration. Alright, let's say I have on benzene ring OH, okay? This is actually called phenol, so okay, it's phenol. It's also a common name that you will learn in organic too. The phenol is reacting with HNO3 in presence of H2SO4. H2SO4 is a catalyst here. OH, you open the table, is a activating substituent and therefore it can be ortho or para. Let me do an example. One is ortho, okay? And so we have here OH, I'm adding on the ring NO2 plus H2O. This is the overall reaction of nitration. Nitration means that you are adding HNO3, which you know is the nitric acid. Okay, mechanism. Alright, so you know that the nitric acid is a strong acid, very strong. So the first thing that we do in this mechanism is a little bit different than the previous ones. Number one, formation of the rhenium ion, okay? So one thing I want to say to you that, you know, HNO3 is a strong acid, can be split into NO2 plus and OH minus. If you put together these two polyatomic ions, you get HNO3, okay? So now, formation of the rhenium ion. I'm going to take my phenol and is reacting now with NO2 plus. That's the slow step. 2 electrons, they attack motion number 1, NO2 plus. N is positive charged. What do we form? The rhenium ion. OH here, the NO2 goes here, so you have an H and a double bond. So that's what we form, the rhenium ion. Step 2, restoring the ring. I am restoring now the ring. I take this, OH, I have the H, NO2, double bond, double bond. What I'm going to use to restore the ring, I'm going to use the OH minus. Okay, remember I had HNO3, I split in NO2 plus and OH minus. 2 electrons, take the H, motion 2, and this one goes inside, motion 3. What do I get? Double bond, double bond, double bond, OH, and NO2, plus H2O. Okay, and I'm done. I'm done because I got my compound. Again now, why this OH is ortho, why is not meta, why ortho. Okay, I start from the rhenium ion. The rhenium ion was this. Oh, remember you have H, you have NO2 here, and you have the bond. Of course you have an H. Play with the resonance structures. Double bond, OH here, H, NO2, and so this one becomes plus. Play with the resonance structure, double bond, OH, NO2, and NH. Do I have another resonance structure? Yes. The plus is here. You can use these two electrons to have this one. Double bond, OH, keep 2, plus, NO2, and then H, and H, double bond. Which one is the most stable? This. Why? Because the plus is outside the ring, because all the elements have reached the octet. The same explanation I gave you before when we were dealing with chlorine. Okay? Now, you can do yourself a meta. You will see that with the meta, you will never end up with this, the most stable structure or resonance structure. Okay? So I'm done with my reactions. Of course, all of this requires a lot of practice.